All right, our next example is solving. So example 3 is going to be to solve this quadratic equation. We have 2x squared minus 15 equals 65. And what we did in the past was we took this equation, we got all the terms over to the left-hand side, and we tried to factor it. Well, you'll notice that we don't have a b term. We don't have an x term at all. We just have an x squared term. And so what we can do here is simply we don't have to factor. We definitely could, but we can just simply isolate the squared term. Once we isolate the square term, we'll be able to just take a square root of that, do the inverse of that, and we'll be able to solve the problem. So in a problem like this, we got 2x squared minus 15 equals 65. All I'm going to do is I'm going to try to get x squared by itself. So I'm going to add 15 to both sides. I'm going to get 2x squared equals 80. I'm going to continue this by dividing by 2. And now I'm going to get x squared equals 40. Okay, so now we're at this stage where how do I get that x squared to just become an x? Well, I'm going to do the inverse operation. The inverse operation is to take a square root of the left-hand side, and also the same thing on the right-hand side. So when I take the square root of something that's already squared, I'm just going to get x. That's just going to make it an x. On the right-hand side, what we have to do here is, because we have an equation here, there's actually two different roots that could work here. We have to put a plus or minus here. Right? There's two different roots that can work here, a plus or a minus the square root of 40. That would work in this equation. Now, if we wanted to on our calculator, we could simply approximate this answer. We could approximate the square root of 40 is approximately 6.32. Okay? If the problem called for that, we could keep it like that. In this case, and in this section, we are going to keep this in simplest radical form. So, for example, this is our answer, plus or minus root 40, but I want to reduce root 40 as we did the previous problems. So the square root of 40 we would reduce, and we would think about a perfect square in there, and we would say something like, okay, this is going to be root 4 times 10, because 4 is a perfect square, right? So root 40 would become 2 root 10. That's as far as I could go, because the square root of 10, there's no perfect square in there inside of that. So the answer to this, going back to my problem, that plus or minus would still exist here. So plus or minus root 40 would become plus or minus 2 root 10. And again, this is simplest radical form, which is an exact answer, right? An approximate answer would be plugging that into our calculator and getting that to be like approximately 6.32. Okay, that's not an exact answer, because we're going to have to basically just round that to the nearest whatever, and then we lose some of that value. So again, what we're practicing is working with these radicals and keeping it in simplest radical form. All right, let's try another one. So this one right here, we have 1/5 times x minus 4 squared equals 11. So what do we want to do here? So if I give this, if I were to give this to you, a lot of people would immediately want to start to like FOIL or distribute this. They'd want to see this as, okay, well, 1/5. Let's go ahead and multiply this out and start cranking that out like that. which you can do. You could multiply, distribute that out. You could put that into standard form, and then you could think about, factoring it or doing something else with it. You definitely do not have to do that, though. So I would try to remember that if we just have a squared term here, we can isolate it. So this right here is the squared term, right? X minus 4 is the squared term. So if I get that by itself, you can actually make this problem shorter and just take a square root and finish it up quicker. So if I get x minus 4 squared by itself, I could get rid of this 1/5 right here by multiplying by 5. Okay, by multiplying by its reciprocal, right? So then I can multiply it by 5 on the other side. This would go away. That would cancel to 1. And I would be left with x minus 4 squared equals 55 now, right? And now what I could do is I could get rid of that square without having to expand that just by taking a square root of the left-hand side and thus taking a square root of the right-hand side. So we know that if I take a square root of something that's already squared, I'm going to take that right there, that x minus 4 is going to come outside, and that's going to be what's left over. So I have an x minus 4 that's now just by itself, and that's going to equal, remember this plus or minus on the right hand side. We're going to have plus or minus the square root of 55. The square root of 55, again, we're going to think about in our head, can I reduce that? Can I reduce root 55? And 55 can only be factored into 5 times 11, and of course 1 times 55. But there's no perfect square that is going to reduce there. There's nothing I can pull out. So this is actually already in simplest radical form. I don't need to do anything else besides that. But I am now going to get x by itself right here by adding 4 to both sides. So I'm going to add 4 to both sides, and my answer is now going to be x equals, and now we cannot combine root 55 plus 4. Those are not like terms that we can just add. So we have to leave these separate. So I would leave this as 4, but plus or minus root 55. So that is my answer. There's actually 2 answers really embedded into this. We're saying that x can be, 4 plus root 55, or x could be 4 minus root 55, which of course have some kind of approximate values. 4 plus root 55 is about 11.42-ish, and 4 minus root 55 is about negative 3.42. Right, those are approximations, so those 2 values still exist there. They're just not nice whole numbers like we did in 4.3 or 4.4, where the numbers just came out super nice, like whole integers. Now we have answers that are not rational. These are irrational answers because we have a square root in them. So there's my answer for this next problem, and that's it.